I will take some time to talk about that, but I also have to cover more things. Did you have a question about something about it, or? Oh, okay.
Actually. Oh.
Okay. Right. Okay, so I think everyone who's actually here now has their test back, which not very many of you. We have 9 people online. It still leaves a lot of people unaccounted for. Oh, okay, now we have.
That's it. That's it.
Well, everyone should be able to see their grades in Canvas. The median score was 78. For reference, also, because of a bonus with the alternating series question, the maximum possible score was 108. That was achieved by 2 students. All right. Now, take some time to know how things were supposed to go. Well, number 1 went pretty well for most part. So there are 2 common answers. You can describe the sequence given. It's either 1 plus 3 over 2n minus 1 n if n starts at 0. But also acceptable being 2n plus 1 over 3n minus 1 minus 1 to the n minus 1 if n starts at 1. And that's why I told you you have to tell me which value of n you're using as your starting value, because that affects the answer. Okay. A lot of people, I didn't take off from this, but a lot of people forgot the parentheses up here. And since you're multiplying by minus 1 to the end, that matters. Okay. A very common mistake that affected a number of problems. There are certain things that we do for sequences and certain things that we do for series. And it says in each problem, do something with this sequence, do something with this series. And you all would get mixed up. You take you'd be asked if a sequence converges or you're using a convergence test for a series. So I did my best to give some partial credit if as much as possible, but you got to keep straight. Which type of problem is it, and what kind of problems are different solution techniques, such as convergence tests, are useful. Otherwise, you're really not doing well out of the gate. Second one was under this series. This sequence. You got me doing it. Convergence or not, and what you should do is multiply and divide by the conjugates. So same expression in denominator except with a plus in between. And what happens is, so you still have the same expression up top. And the denominator simplifies to just 2n. Then what you can do is you can divide top and bottom by, or you can also try L'Hopital's rule, but highest power n in the whole fraction. Now we do have an n squared here and here, but they're under square root signs. So the highest power is actually n to the first. So you can do this. And so then you'll just have 2 down below, and then when you have, if you're dividing by n, that's the same as dividing by n squared under the square root sign. So you end up with 1 plus n plus minus 1 over n. Someone's making noise who's attending online. Can you please mute yourselves? Okay. All right. So it does converge and converges to 1. We use about growth rates of functions. The sequence you were given is e to the n over n to the 10. Now you have an exponential up top and a polynomial function down below. They both grow, but exponential functions grow faster than polynomial functions. And based on relative growth rates, this goes to infinity. So it diverges. The last question that concerned sequences before getting into series, you have sequence where the terms are flipping. You have n cubed plus 3n squared plus 2n plus 1. Now, a practice test had something similar like this, but in the practice test, you had same power of n above and below. And then the -1 to the n caused it to flip between 2 values, so it diverged. But here, the denominator has higher degree than the numerator. So because of that, the denominator is growing faster than the numerator, so the whole thing is going to 0. So even with the sign flipping, it's just flipping signs around 0. So this sequence converges, and the limit is 0. The question's on these first 4. Okay, next was a geometric series question. It's to infinity, 4 minus 3/4 to the n. So this is a geometric series where r is equal to the number that's being raised to the nth power, minus 3/4. A lot of people made sign mistakes about this minus 3/4. Like even if they wrote down minus 3/4, then they applied it wrong in the formula. Gotta watch your signs. And then the remember, a is always the first term, but notice it started off n equal to 2. So a number of mistakes were made there. So a is going to be 4 times minus 3/4 squared, which is 9/4. So then the sum, so first, because r is equal to minus 3/4, that alone tells you that at least the series converges. As for what it converges to, okay, a over 1 minus r, and then so a lot of people not realize that this is 1 plus 3/4. This fraction simplifies to 9/7. That's the sum in that case. Okay. This one is a telescoping series. And plus 1, so it's necessary to do partial fractions. And what happens when you do that is it gets 1/2 1 over n minus 1 minus 1 over n plus 1. So then you work out, if you write out for several terms, you start seeing what cancels. What you end up with is the 1/2. When n is equal to 2, you get a 1. And then when n is equal to 3, you get a 1/2. Everything else eventually will cancel. So the sum turns out to be 1/2 times 3/2. So the sum is 3/4.
So, if a telescoping series, does it not matter when the series starts, like, and starting value and
Oh, starting value matters very much. Yeah. The only time it really doesn't matter is if you're dealing with a sequence and you want to know if a sequence converges. But yeah, if you start with enough different value, okay, starting value would not affect the question of convergence versus divergence. It affects the value of sum. Okay, that's a halfway point. Are there any questions so far? Okay. Okay, now we have sum to infinity 1 over n times natural log of n squared. This is a candidate for the integral test. We look at the integral from 2 to infinity of 1 over x natural log of x squared dx. And to evaluate this integral, you can use a u substitution. You let u equal natural log of x, so then du is 1 over x dx. So you end up with the integral of 1 over u squared. And you can see that integral, I won't go through the rest of it, but the integral converges, therefore the series converges. Try something like a ratio test on this. It's going to be inconclusive. It'll give you a value of 1. Next. 2 plus 2 squared plus n plus 1. So here we have a polynomial over a polynomial. What do you do for this? Is you do limit comparison tests. And to determine which series you're going to use a limited comparison test with, you look at the degrees. Here we have n squared up top, n cubed down below. So because the denominator is degree 1 greater than the numerator, you limit comparison with 1 over n. And because 1 over n is a harmonic series that is known to diverge, this series diverges too. Okay, number 9. So this is an alternating series. The terms are certainly going to 0 as n goes to infinity, and then throw in a sign flipping. So this converges by the alternating series test. Yeah. And then the bonus, you have you look at the absolute value of each term, and in place of n, you plug in, like, look at n plus 1. And you want that to be less or equal to 10 to the minus 6. So you take that inequality and you solve it for n. And that is, so that'll tell you how many terms you need to be sure that you're within 10 to the minus 6 of the exact sum. A fair number of people got that, so that was good. Final three. N over n factorial to the n plus 1. So this is the candidate for the ratio test. Supposed to determine if it converges absolutely, conditionally, or diverges. When you're looking at the limits, then goes to infinity. Then you have n plus first term. Divided by the nth term. And when you simplify that as much as you can, 3n plus 1 over 3 to the n plus 1 over 3 to the n gives you 3. And then you have 2 to the n plus 2, denominator, 2 to the n plus 1 in the numerator, so that simplifies to 2 in the denominator. Now, some people took that and said, oh, it's greater than 1, it diverges, but the factorial is what's decisive here. Because you have n factorial up top, n plus 1 factorial down below. When you simplify that, you get a factor of n plus 1 in the denominator. So if you take the limit of this, n goes to infinity, it's going to go to 0. Therefore, it converges absolutely. Condition, a lot of people could put conditional. Conditional convergence generally only comes up if the series has sign flipping involved. Because if you have a series that has all positive terms like this, and you determine it converges, that convergence must be absolute. Because you're taking the absolute value of it, and that's the same thing. Remember, n factorial is 1 times 2 times 3 up to n. N plus 1 factorial is 1 times 2 times 3 up to n plus 1. You simplify that, the n plus 1 is what remains. All right, now the power series ones. All right, here radius unitable convergence for this power series. Minus 1 to the n, that's equal to 2 to the n over n 2 to the n. So to determine radius of convergence, at least, we use a ratio test. So you'll have, I'm going to ignore the minus 1 to the n part because we're taking the absolute value of the whole thing anyway. So when you simplify as much as you can, that n over n plus 1, that's going to 1. So that's not going to really affect things. You're going to have x plus 2 up top. And then because you have this 2 down below, that you're going to have that. So that turns out to be the limit that the ratio test gives you. And you want this to be less than 1 for convergence. So you have x less than 2. So the radius of convergence is 2. Now, because the center is at -2, then you really are considering x from -4 up to 0. The interval of convergence turns out to be x strictly greater than -4, less than or equal to 0. Also can be written this way. Parentheses -4, 0, with a square bracket after the 0. The reason why is if you plug in x equal to 0, the 2 to the n's cancel, and you end up with an alternating series that converges. If you plug in x equal to -4, you end up with a series 1 over n, which diverges. So it diverges at this endpoint, it converges at this one. Questions before I do the last one? Okay. Survey 12 was meant to be a doozy. Function you're given is natural log of 1 minus x squared, and find a power series for this and find out those radius convergence. The hint you're given is find series over derivative. I gave you a derivative, so minus 2x over 1 minus x squared. Now, this function you can think of as a sum of a geometric series, where r would be equal to x squared, and then a would be equal to minus 2x. Okay. Now we need r to be less than 1 in absolute value. So we need absolute value of x to be less than 1. That tells you that the radius of convergence of this series is 1. So since the derivative is a sum of a geometric series, you just go ahead and write out what that is. So sum from 0 to infinity of minus 2x times x to the 2n, because it's r is equal to x squared. Now I'll clean this up a bit. So minus 2x to the 2n plus 1. So that's the series for f prime, and we know its radius of convergence. So I need you to tell me, if I have a series for f prime in hand, and I want a series for f, what do I do to this series to get it?
Take the integral.
Integral. A number of people took the wrong way and took for derivative. If you're given a series, if you have a series for derivative, then you have to go back. You have to go the other way. So the original function so what we get is so minus 2, and then let's use the power rule on each term. Okay. This can be simplified, but I'm not concerned about that. I wouldn't care for giving points anyway. Now there would be a plus c, although if you plug in x equals 0, turns out that the c turns out to be 0. So I wasn't concerned about that either. I figure if you get this far, that's quite good. You deserve a point. Now, the radius of convergence from a derivative is 1, but when you take a power series and you do term by term integration or differentiation, neither one of those, it does not change the radius of convergence. So it would still be 1. Or if you didn't remember that, once you got to this point, you had the series, you can just do ratio test on it directly. and also conclude that radius is 1. And that's it. All right. So when you look at your test, if you have any questions about, why points were lost, certainly can, talk to me after or whatever. And because there's always a possibility, you never know if I might make a mistake. After grading 31 of these in total. Any questions about this one? All right. Now, certainly, this test was a blow for the grades of some. And the midterm accounts for 30%. But keep in mind that there's still hope because there's still more homework to come. Also, the final is not comprehensive. You're not going to see any of this stuff in the final. The final is going to be on new material, dealing with very different topics, vector operations, parametric curves, things like that. Things that, based on my experience teaching this class in the past, students generally had a much nicer time with. So if you're not happy with how your grade stands now, you still have a legitimate opportunity, which you don't necessarily get in math classes, because of course everything just keeps building and building and building on what you had. But now the Cal 3 is a little different because there's a break, and now we're just going to see all different things, and we have a chance to save yourself. All right. Okay. And to mark the occasion of not having to suffer through sequences and series, and especially power series anymore, the traditional Cal 3 No More series cupcakes will be given in class a week from today. So I'll be kidding about that. Also, I'm starting to create the next few homeworks. And one thing I'm starting to do is, actually, I think I said at the beginning of the semester, there are going to be 16 homeworks in total. It's gonna have to be a little less than that. I guess certain assignments that I would have given before, separate assignments, I'm gonna combine into one. And the reason for that is I didn't want a situation where we have due dates bunching up. Make sure there's at least some gap in time between assignments. So we're probably gonna be more like 13 or 14 altogether. But the whole ball of wax counts for 30%, but it doesn't really change how many problems I was going to give in total. Just redistributing when they're due, so they do not want with much homework all at once. Now, to begin with, the new stuff. There's a lot more visualization going on. In what we're covering now, because you're accustomed to working from Cal 1 and Cal 2, working in 2 dimensions, like graphing y equals f of x. In Cal 2, you would have seen some 3-dimensionalness. For instance, you've worked out integrals for computing volumes of solids, so it would be a good idea to try to be able to visualize 3D solids. So now we're going to see more things going on in three-dimensional space. So. Okay, actually gonna do a contrast here. So what you're accustomed to is just the XY plane. So here we're sitting in 2 dimensions. So you just have some points XY that you get by taking the vertical distance between your point and the x-axis, and also the horizontal distance between the point and the y-axis, and of course a sign difference where you'd have negative x values over here, negative y values down here. You also had quadrants labeled 1, 2, 3, and 4. Apparently using Roman numerals, not sure why. Indicate corresponding to whether x or y was positive or negative. So positive and both positive x and y values would be quadrant 1, and so on. Now, possible that when I was babbling about distance between axes, I might have said something wrong, just because it's a bit off the cuff. But anyway, y coordinate is distance from the time distance from the x-axis. X coordinate plus u is sine distance from the y-axis. Okay, and when I say sine distance, I mean the distance it can be positive or negative, depending on your orientation. So to contrast with that, looking at 3D, of course, a lot more difficult to visualize because I'm drawing on a 2-dimensional surface. So unfortunately, depth perception is needed. So if I have, my x-axis here, y-axis here, and then I have the z-axis going up and down. So now, if I was up here looking down, I'd be looking down at the XY plane that you see here. And I also have to be clear about which direction is positive, which direction is negative. When we look at the XY plane, there's a general understanding that x-axis, we're going from left to right, from negative to positive, and then for y-axis, it's from bottom to top, going from negative to positive. The picture I've drawn here, three-dimensional space, you can't really be sure. So I'm going to specify that here. So let's go to plus infinity in this direction, minus infinity in this direction for x, and then and increasing y values going in this direction. So I'll use arrows to indicate which way we're going, from negative to positive. Z is more self-explanatory. It makes sense that gonna have going up for positive values.
Is he always on top?
Um,
Look, graphs I've seen, it's like the X where the Y is, the Z is where no, I'm sorry, the Y is where the X is, the Z is where the Y is.
it just depends.
Okay.
Yeah, for different conventions. And actually, I only chose this convention because that's what I have in my notes, which comes from plotting something in MATLAB. So, yeah, and that's why we have to be careful and check, which way it is. There's a lot less agreement when it comes to 3D. 2D, everything is really nice and standardized. So I think I made a point about this some time ago, that since XY plane is divided into 4 quadrants, in 3D, you can divide three-dimensional space into 8 octants. So, so X, Y, and Z all positive, that would be labeled as the first octant. But I can't really talk about the other octants because mathematicians have not been able to agree on what are the meanings of octants 2 through 8. As far as which of X, Y, and Z are positive or negative. So, and you also have a situation where, like, for instance, mathematicians have one convention, physicists have another, and when you teach a class for both math and physics students, it gets really aggravating. Yes, Morgan?
But you're right, X, Y, Z.
Positive.
Yeah.
Yeah, so we only have agreement about what the first octant is. It makes sense, it's when they're all positive, but beyond that, no. Um, so if I want to plot a point, in space, with coordinates, 2, 3, 1. So if find where x is equal to 2, and then y is equal to 3, and then I locate that point first in the x, y plane, so that's the point x is 2, y is 3, z is 0. And then, but I want the point 2, 3, 1. So now from here, I have to go up 1 unit. So right here is the point 2, 3, 1. With everything as much scale as I can get it. Not at all obvious because we're taking 3 dimensions and projecting it onto a 2D board. But that's what we do. If you find your place along each axis one at a time, just like you would do in 2 dimensions, it's at 2 dimensions, it comes so naturally to us. It's good because it's so much easier. But now your depth perception plays a role. I moved from here to here because that's 1 unit along the z-axis. So now we can say that the xy plane is a set of all points of a form some x, some y, and 0. So you could say that really z equals 0, the equation z equals 0, and the xy plane are exactly the same thing. So because the xy plane is all points where you don't actually have a z coordinate or it's 0. So similarly, the yz plane, that's where the odd one out, x is equal to 0. So so this plane right here, where x is equal to 0, like along this line, that whole plane is the yz plane. And if I took this whole 3D assembly and turned it a bit so that I have a y-axis going to the right and the z-axis going up, you can see, oh yeah, that's the yz plane. And then finally, the xz plane is described by the equation y is equal to 0. So you think of the plane is passing through this line right here. So this right here is the yz, sorry, the xz plane. So sometimes it can be helpful to, since we're already projecting 3 dimensions on a 2-dimensional surface, that if I'm taking some point in 3 dimensions and just setting one of its coordinates equal to 0, then I'm projecting that point onto one of these planes. So here at my point 2, 3, 1, this point 2, 3, 0, that is the projection of the point 2, 3, 1 onto the xy plane. And so to get that projection, all you have to do is set the z coordinate equal to 0 and you keep the x and y coordinates the same. Whereas if I wanted a projection of this point onto the, let's say, the yz plane, I'd set the x coordinate equal to 0. So that would give me this point right here, 0, 3, 1, where y is equal to 3 and z is equal to 1. So that's a projection onto the yz plane. Okay. All right, any questions so far, before we go to the next thing? Okay. Rest of what I have today is more algebraic, you might find that nicer to work with. Now, one thing that you'll likely are familiar with from lower level math is the distance formula. Like in 2D, if I have 2 points on x1, y1, then x2, y2. And I'll label the points themselves more concisely. So I'll call that P1 and then the other is P2. Then I say that the distance, so D between P1 and P2, is take the square sum of squares of the differences in coordinates. So x1 minus x2 squared plus y1 minus y2 squared, take the square root. So this basically Pythagorean theorem at work. To find the distance between them. So similar idea, if we're in 3 dimensions. So if I have 2 points, P1 that has coordinates x1, y1, z1. 2 has similar coordinates x2, y2, z2. So generalizes in a logical manner. This is between the two. We look at all 3 coordinates plus 2. We take the sum of squares of difference in x, difference in y, difference in z. Sorry. And take the square root. Example, my first point. What I was doing earlier, 241. I have a second point. 8 minus 5, 0. So in a distance between them. If I look at the differences in the x's, y's, and the z's. And then just writing out from there, turns out to be square root 101, so the distance is a little more than 10. Now, from 2 dimensions, you've often dealt with equations of lines, equations of circles, or inequalities that can describe like the inside of circles or discs. So we have the same things in 3 dimensions. Good question, all right. Okay. Now, we're dealing with planes a whole lot more later. But in general, in 3 dimensions. And generally, an equation of a plane can be described by, so this is a general equation for a plane in 3 dimensions, where A, B, C, D are some constants. Now, just some simple examples of our theme. So for instance, if I set A, B, and D equal to 0, and C equal to 1. And I have this very simple equation for a plane Z equals 0. That's just the XY plane. Here's another. If I set B and D equal to 0. No, B and C equals 0. No, hold on. First stage to a break. And the back will hang over going. So, all right. B and D. I knew I wanted 2 B's to be 0. It's on the right ones. A is equal to 1, and B is equal to -1. So you just get X equals Y. Now, you're familiar with X equals Y, or maybe often written as Y equals X, as a line, but that's in 2 dimensions. So let's say Y equals X. Might be naturally inclined to think of this line here, and this is what it is in 2 dimensions. But in 3 dimensions, you have all possible Z values to consider too. So it's almost like if you took this line and you duplicated it for every Z value from -infinity to infinity. That gives you a plane, not a line. Like I said, we're dealing with planes a whole lot more later, but this is the main idea. Now deal spheres. So, and you dealt with equations for circles before. Now just add one more dimension. So in general, you have the equation of this form: x minus h whole thing squared plus y minus k. But probably seeing this notation, in fact, probably using these letters for describing a circle. But I have to account for z also. So for t minus l squared equals r squared. So this describes a sphere that has a center HKL, x coordinate, y coordinate, z coordinates, and radius r. Just as like in 2 dimensions, we have, for instance, x squared plus y squared equals r squared. You know, the circle centered at the origin of radius r. So we just add another term for z. Like simplest example, one of both interest, a unit sphere. He said a center equal to 0 and radius is equal to 1. So you just get x squared plus y squared plus z squared is equal to 1. So a sphere consists of all points that have distance r from wherever the center is. Now, if I change that equals to a less center equal to, that would be I have to refer to it as a ball. So you're including the interior of the sphere. So as another example, if I have sphere center -3, -1, 1, and radius r is equal to 10. So that means we have x plus 3 squared plus y plus 1 squared plus z minus 1 squared is equal to 100. A lot of mistakes come about from forgetting that the radius is supposed to be squared. So keep it in mind, it's all these terms are equal to r squared. Now, if I really wanted to, I could go ahead and expand those out or FOIL them. Now, what that would give me is x squared plus y squared plus z squared plus 6x plus 2y minus 2z is equal to 89. Now, the trouble of having an equation of sphere written like that is it's not obvious what the center is or what the radius is. Really, the only way that you can tell me to even have a sphere is if you have x squared, y squared, z squared terms in your equation, and notice that all of them, they have the same coefficients. So that's how you know it describes a sphere as opposed to something else. What kind of shape do you think this equation would describe if the x squared, y squared, z squared terms had different coefficients? That would not be a sphere. What might that be instead?
3D oval.
I heard a 3D oval, that's apt. I also heard ellipsoid, yes. Yeah, that's a technical term, but yeah.
Okay.
But later we'll talk about a shape called a parallelepiped. But actually, we turned to Wikipedia to see how it's supposed to be pronounced. You have a funny Wikipedia guy saying parallelepiped, but some students opted to call it a parallel box. So, yeah. Okay. Now, the thing is, suppose that you are given an equation like this, where you can examine it and tell that at least it's a sphere, but you don't know just by looking at the equation what the center and radius of that sphere are. That we can do some algebra to find out. So as an example, I have this equation. 4x squared plus 4y squared plus 4z squared. 8x minus 16y minus 16 equals 0. So the goal is to get this equation in a form like this, where we can just read off what the coordinates of the center and radius are. So first thing you should do is group terms according to x, y, and z. So all the x terms together, all the y terms together, all the z terms together. So I'm just going to write these terms in a different order. So the x terms, then y terms, then we only have one z term. Then we have this minus 16, and it's going to move that to the other side. Okay. Then notice here we have x minus h, y minus k, etc. as perfect squares. So what do we do? What do we need to do to this to try to get it in a form like this? Completing the square, yes. Right. And if you don't remember how to do that, you have x squared plus bx plus c, where we make it so that the leading coefficient is 1. That could be written as x plus b over 2. There's your square plus c minus b squared over 4. Okay, so we're gonna make use of that here. So here you're gonna factor out a 4, and then here I'm also gonna factor out 4. Actually, yeah, every term is divisible by 4. Let's just go ahead and do that. X squared minus 4x plus y squared minus 4y. No, it's 2x. Plus z squared equal 4. And now this formula I can use on the terms involving x and also involving y. So this would be the same as x minus 1 quantity squared. And then in this case, I don't have a constant term over here, so c is 0. And then I'm going to have minus 1. So that comes from the x terms. And then from y terms, similar thing, you're going to have y minus 2 quantity squared. And then subtracting off 4. And I have squared. So now all I need to do is move all constant terms over to the right side. Now I have x minus 1 squared plus y minus 2 squared plus z squared. So I have minus 1 minus 4 move over to the right side and I get 9. So now I have the equation, the standard form of the equation for a sphere, and that tells me what the center is. So center is 1, 2, 0. And what is the radius? It's 3. You gotta take the square root of what you have over here. Okay. This is how you go back and forth between the two different ways of common ways of writing the equation of a sphere. Any questions on how this one played out? Okay. All right. A couple more examples. I can describe certain regions in three-dimensional space. So suppose one statement that describes all points between, and I want to emphasize here, not on the spheres centered at this point. So in other words, two concentric spheres. So centers and located at -1, 1, 2. And radii 3 and 5. So all points that lie between those two concentric spheres. So that means points that are outside the sphere of radius 3, but are still inside the sphere of radius 5. So if I write this expression, x plus 1 squared, so I'm accounting for the center. Okay, so this would describe the square of a distance between x, y, z and the center. I need that distance to be strictly greater than 3. Notice I said not on. If I could allow for points to be on that sphere, I would have greater than or equal to. No, this is wrong. Fix my mistake.
It would be greater than or equal to, right?
It's
Because,
not on sphere,
okay,
but there's never a mistake.
Square it.
Yeah,
um,
yeah. See? All right. And then make sure it's still inside the sphere of radius 5, or I need to put,
halfway.
okay. Yeah, so if they're allowed to be on, then I'd have less than or equal to. Questions about that one? Really, it's 2 inequalities. This is that because these 2 inequalities have this expression in common, it's feasible to write it in this concise manner. Whereas suppose I had 2 spheres that did not have the same center, and I wanted to be outside one and inside the other, then I really would need 2 separate inequalities for that.
Let's say radii or just.
Yes, radii. Okay. Last example. Suppose we have an inequality given to us, but we want to understand what this inequality is saying geometrically about the points x, y, and z that satisfy it. Squared plus y squared plus z squared is greater than 4x. Now, if I didn't have 4x here, if I just had a number, then that would mean I was describing all points that are outside a sphere of a given radius, but I don't have a constant, I have 4x. So I want to be able to describe this in such a way that I can relate to a sphere, wherever that sphere's center is. So to get a handle on what this equality is describing, I need to complete the square again. So if I take this minus 4x and move it over, and then I complete the square on it. So x squared minus, so using that same completing a square formula that I wrote down earlier, I'm going to take this half this coefficient of x minus 2 quantity squared. But the thing is, if I were to square this out, I would have x squared minus 4x plus 4. But that means I need to subtract off 4 to offset it. So this right here is equivalent to this. You get that from applying that completing the square formula I gave earlier. But then I can take that minus 4 and just move it to the other side. And that's going to tell me about radius. So who could tell me how can I describe all points x, y, and z that satisfy this inequality the way it's written?
Right, so center is -2, 0, 0, and the radius is 2.
Almost.
Almost. Oh, yeah.
So I just-
Oh, no, sorry, what did you say earlier?
Oh, me?
Yeah,
Yeah, so the center is at -2,
Okay.
0, 0,
possible.
and the radius, or +2, excuse me.
Yeah,
I
it's get
I
distracted.
had it wrong. Yeah, sorry. +2, 0, 0, and the radius is 2.
Yeah, and you were saying as Paul points outside, yes. Yeah, but because it's strictly greater than its point outside that sphere that you described. Okay, so. The way of writing it is. The upwards X, Y, and Z such that. Such that X, Y, Z is outside. And not on, so strictly outside. Outside sphere. The center. 2, 0, 0. Radius is a square root of this. Which is 2. Okay. So. To go to show from these examples. Never forget your algebra. Okay. Well, I've come to the end of my notes. What's about anything? Do you test? I'll put that time anyway. So, all right, so I'll keep going with vectors on Wednesday. Very good. Okay.